Welcome to your custom deep dive. Today, we're going to be diving into the quantum realm.
Okay.
Don't worry.
You're right.
We're going to make sure everything makes sense, even if you've never heard of like a photon before.
All right.
So our focus today is on some really cool research that's coming out of Seoul National University. They're doing some really, really amazing things with light.
Right.
But not the kind of light that you use to,
Right.
light up your living room. Or
Exactly.
imagine if you could take like your flashlight and swap out the regular bulb with like pure quantum energy.
Okay.
That's kind of the level we're talking about here.
I see.
And just like you can, get a more powerful bulb for your flashlight,
Right.
they're looking at ways to make these quantum light beams stronger, more intense, more...
Pump up the volume.
Yeah, exactly. Pump up the volume.
Yeah.
And the cool thing is their research compares two completely different ways to do that, to actually amplify this quantum light.
Interesting.
So we're talking about like two different techniques.
So essentially amplifying quantum states.
Yeah.
Okay.
Exactly. Amplifying quantum states.
Yeah.
Which is kind of a mind-blowing concept when you really, really think about it.
It's like comparing turbochargers for your quantum flashlight.
Okay.
You know?
Like that. I like that analogy.
Yeah.
So before we get into the how, let's talk about what they're amplifying.
Sure.
So the paper focuses on two types of quantum light.
Okay.
The first one is called hybrid entangled states.
Okay.
Or HES for short.
Right.
And the second one is superpositions of coherent states.
Okay.
Or SCSs.
Gotcha.
So we've got HES and SCSs.
Right.
Let's start with HESs.
Okay, so HS, hybrid entangled states, these are really interesting because they sort of bridge the gap between two very different ways that we think about light.
Okay.
So think about like a dimmer switch where you can smoothly adjust the brightness. Right. Now imagine combining that with a simple on-off switch.
Okay.
That's kind of what an HES is like. It mixes this continuous wave-like nature of light with the discrete particle-like behavior of photons.
So it's like they have 1 foot in the classical world of like light waves and 1 foot in the quantum world.
That's a great way to put it.
Of like individual photons.
They exist in both worlds at the same time.
Okay.
Now, SCSs, those superpositions of coherent states, those are a whole other ballgame.
Okay.
Imagine multiple flashlight beams, each with its own wave pattern, all overlapping.
Okay. And
when these waves interfere, it creates some seriously bizarre results.
So it's like each beam of light has like its own agenda.
Exactly.
Like I'm going to do my own thing.
You get this unpredictability because you're dealing with multiple possibilities existing at once.
Okay, and this unpredictability, that's where choosing the right amplification method becomes really, really important.
Absolutely.
So the researchers in this paper, they specifically looked at two methods.
Okay.
One is called, and this is going to sound a little technical, but we'll break it down. It's called the ḥaːa method.
Okay.
And essentially what they do is they add a photon, a particle of light, and then they subtract one. Okay. So it's like a +1 -1 kind of thing.
Okay, yeah.
The other method is called the ḥaːa method.
Okay.
And with this one, they just add 2 photons in a row.
Right, so it's like a double shot of espresso.
It is like a double shot of quantum espresso.
Exactly.
So you've got these two different approaches to like boosting the signal, boosting the light.
Ramp it up, yeah.
And what they found is that HESs and SCSs, they react very differently to these methods.
Interesting. So how so?
Yeah, so...
Yeah.
Yeah, so how do they react differently?
Well, with HES is actually pretty straightforward.
Okay.
Amplifying them, it's surprisingly similar to amplifying regular light.
Interesting.
The same principles apply no matter how many photons the HES is entangled with.
So even though they have this like quantum side, they still kind of remember how to behave like regular light.
Exactly. But with SCSs, things get a lot more interesting. Their behavior is much less predictable.
Right.
It's like each of those overlapping beams we talked about has an opinion on how the amplification should work.
And that makes choosing the right method.
Yes.
Whether it's adding, then subtracting a photon, the ḥaːa method, or adding 2 in a row, the ḥaːa method.
Exactly.
That becomes even more important.
Absolutely.
Okay.
Now, remember how we talked about that unpredictable nature of SCSs? Well, there's a kind of hidden order in there.
Okay.
Each SCS, despite being made of these multiple beams, has a preferred number of light particles.
Hold on. Preferred.
Yeah.
like they're picky eaters or something.
That's a great way to think about it. And this preference, it really matters.
Okay.
It directly affects how well the amplification works.
Interesting.
It's almost like the SCSs put up a fight if you try to change their preferred number too much.
So they're like, nope, this is how many photons I want, and that's it.
Exactly.
And that resistance, that fight,
Yeah.
that has a real impact, right?
It does.
Doesn't it affect how much information you can get out of these amplified states?
It does indeed. And the researchers measured this
Okay.
using something called quantum Fisher information.
Okay, now we're getting really technical.
A little bit.
Yeah.
But think of it like this. Imagine you're trying to take a picture
Yeah.
of a hummingbird's wings
Okay.
as it's hovering there.
Okay.
The sharper the image,
Yeah.
the more information you have about those wings, right?
Right.
Quantum Fisher information is kind of a measure of that sharpness, but for quantum states.
So the higher the quantum Fisher information,
Yeah.
the clearer the signal.
Yeah.
The more useful these amplified states are for things like, precise measurements.
Precisely.
Okay.
And what the researchers found is as you increase that preferred number of photons in an SCS,
Yeah.
this quantum Fisher information, our measure of sharpness,
Yeah.
it starts to fluctuate.
Fluctuate. So it's not a simple case of more photons equals worse information.
Not at all.
Well.
For certain SCS configurations, the ḥaːa method, which we might expect to work best for low energies,
Yeah.
can actually outperform the ḥaːa method even at high energies.
Wow. So even with a higher preferred number of photons,
Yeah.
you can still get a really clear signal,
You can.
depending on the amplification method.
Exactly.
That's pretty counterintuitive.
It is. It's a great example of how the quantum world doesn't always follow our classical intuitions.
Right, right. It's like it's playing by a different set of rules.
Exactly.
So to sum it up,
Yeah,
with HESs, amplification is pretty straightforward.
pretty much.
But with SCSs, it's all about finding the right method
Right.
for the specific state
Mm-hmm.
and its preferred number of photons.
You got it.
Okay.
Okay, this is where things get even more interesting.
Oh, how so? Okay, so how does it get more interesting?
Well, up until now, we've been talking about these quantum light states.
Right.
Like, they only have one setting, so to speak.
Okay.
One preferred number of photons.
Right.
But imagine if they could have multiple settings,
Okay.
multiple preferred states,
Multiple.
all at the same time.
So we're going from like a dimmer switch to like a whole control panel here.
That's a fantastic way to put it, yeah.
Okay.
And the researchers found that as you increase the number of these settings in an SCS,
Yeah.
those fluctuations in quantum Fisher information we talked about,
Right.
they get even more dramatic.
So more settings, more chaos.
It's not pure chaos.
Okay.
The researchers found that even with all this complexity,
Yeah.
the choice of amplification methods still matters tremendously, depending on the SCS and how it's configured.
Yeah.
One method might give you a crystal clear signal, even with lots of settings,
Okay.
while the other might result in just a jumbled mess.
So it's like choosing the right tool for the job, right? Sometimes you need a scalpel.
Yeah,
Sometimes you need a sledgehammer.
absolutely.
It depends on what you're trying to do.
And understanding which tool to use is going to be crucial as we move towards these even more, complex, higher dimensional quantum states.
Right, because this isn't just about making brighter flashlights anymore.
Exactly.
This is about
Yeah.
quantum computing,
Quantum communication.
where having the wrong tool for the job could just completely derail everything.
Absolutely. The tiniest error can have huge consequences.
So if our listener is walking away from this deep dive,
Yeah.
what's the one thing that you want them to keep in mind?
I think the biggest takeaway here is context is everything in the quantum world.
Yeah.
There's no magic shortcuts. There's no one-size-fits-all solution.
Right.
You really need to understand the specific state you're working with, the tools you have at your disposal,
Okay.
and ultimately, what are you trying to achieve?
What's the end goal?
Yes, exactly.
Be deliberate. Choose the right tool for the job.
Absolutely.
Knowing that sometimes a gentle nudge is better than a giant push.
Couldn't have said it better myself.
Well, this has been a fascinating deep dive.
Yeah.
I feel like my eyes have been opened.
It's a wild world down there.
It really is. The quantum world is full of surprises.
It certainly is.
Well, to our listener, we hope you found this journey as illuminating as we have.
Yeah. Thanks for listening.
Until next time.
Ever try to listen in on a whisper when you're in a room full of people?
Yeah.
It's almost impossible, right?
Yeah.
That's kind of what it's like for scientists when they're trying to look at the quantum world.
Right.
The signals are so faint.
Yeah.
So today we're going to dive into how they actually amplify those signals.
Okay.
And you might be surprised to learn there are actually different flavors of quantum information.
Absolutely. It's not like a one-size-fits-all kind of deal.
Right.
This particular paper looks at two really important types of quantum states.
Okay.
Hybrid entangled states,
Mm-hmm.
or HES for short,
Okay.
and then superpositions of coherent states,
Okay.
or SCSs.
HESs, SESs?
Yeah.
Sounds pretty sci-fi to me.
A little bit, yeah.
Can you break those down? What are we actually trying to amplify when we talk about these things?
So if you think about a HES,
Okay.
it's really like a combination.
Okay.
It's like a mix of two completely different types of quantum information.
Interesting.
On the one hand, you have what's called a discrete variable,
Mm-hmm.
which is kind of like a fixed quantity.
Okay.
So think of it like if you have two cookies,
Okay.
you can't really have half a cookie in that case.
Two cookies, got it.
Right.
What's the other part of the mix?
So the other part is what's really interesting is a continuous variable.
Okay.
And this is more like a wave
Okay.
that can have a whole range of values.
Okay.
So think of it like the frosting on top of your cookies.
Okay.
You can have a little bit of frosting or you can have a lot of frosting.
So it's like a cookie with a specific amount of frosting. You can't change the cookie,
Exactly.
but you can change the frosting.
Exactly.
Okay, got it. What about SCSs? How do they fit into this whole cookie analogy?
So imagine you take those frosted cookies
Okay.
and you create a blend
Uh-huh.
of different possible cookie frosting combinations.
Okay.
So an SCS is a quantum state that's simultaneously representing all those combinations
Well,
all at once.
okay, so you're like blending cookies and frosting together in every way imaginable.
Kind of, yeah.
My brain's trying to keep up.
Yeah, it's a lot.
But why is it so important to amplify these states? Like, what's the big deal if these quantum whispers just stay really quiet?
So it's not just about making them louder, it's about making them clearer.
Okay.
You know, imagine using a super sensitive microphone
Okay.
to be able to pick up that whisper in that crowded room.
Right.
Amplification helps us study these states with more precision,
Okay.
and it really unlocks new possibilities in quantum technology.
So how are scientists actually amplifying these states?
So the paper looks at two main techniques.
Okay.
One involves adding a particle of light, a photon,
Mm-hmm.
and then very quickly taking it away.
Oh, wow.
So it's sort of like taking a quick peek into the quantum world
Right.
and then quickly closing the door.
It's like you're not really supposed to be in there, but you're just taking a quick look.
Exactly.
Okay, and what's the second technique?
The second one involves adding two photons in a row.
Okay.
So it's like you're giving it a double dose of energy.
Okay, got it.
Yeah. Now, the paper found something pretty surprising about how HESs behave during amplification.
Yeah.
Right.
They found that the fidelity and gain for HESs,
Okay.
basically how accurate and strong the amplified signal is,
Gotcha.
behaves very similarly to how they behave for simpler states called coherent states.
Interesting.
And that's surprising because HESs are much more complex.
Right. They'd be totally different.
You'd think they'd be completely different, yeah.
Yeah.
So that was unexpected.
It's kind of like when you have like a gourmet recipe that has like a dozen ingredients.
Right.
But it ends up tasting like a grilled cheese.
Yeah, exactly.
So what's the explanation for this?
Well, it seems like the more complex structure of the HES doesn't really matter as much as we initially thought.
Okay.
It's as if that discrete variable part, that fixed cookie part, acts like a label,
Okay.
while the continuous variable part, the wave-like frosting, is what's
Yeah.
really getting amplified.
Okay, so we've got HESs acting like we kind of expect.
So far. What about the SCSs, those blended cookie frosting things? Are they as straightforward?
Not quite.
Uh-oh.
Amplifying SCSs is where things get a lot more complex.
Here we go. Hit us with it.
Yeah.
What makes them so different?
It really comes down to how sensitive SCSs are to their initial starting conditions.
Okay.
The number of components in that blend their phases.
Mm-hmm.
Even the tiniest details can drastically influence how they behave during amplification.
So HES is predictable, but SCSs are kind of like the wild cards?
Exactly. They really keep us on our toes.
Wow.
Which is part of what makes this research so exciting.
Yeah, I bet.
And this is where we bump into the concept of pseudo-number states.
Pseudo-number states.
Yeah.
Okay, that's another sci-fi word.
I know, right?
What does that even mean?
So remember how we said that SCSs are like that blend of different possibilities?
Yeah, like the different numbers of photons.
Exactly.
Yeah.
Different numbers of photons.
Okay.
Well, despite being this mix,
Yeah.
they sometimes behave as if they have a well-defined number of photons,
Mm-hmm. Uh-huh.
even though they technically don't.
Wait, so they're pretending to be something they're not?
Kind of, yeah. It's very strange.
That's so weird. Why does that even matter for amplification, though?
So that pseudo-number directly affects how accurately we can amplify these SCSs.
Oh, wow.
It's almost like if you're trying to hit a moving target.
Okay.
The better we understand its quirks, the better our aim is going to be.
Right.
And this is crucial if we want to use SCSs for building, those really sensitive quantum technologies we were talking about earlier.
Right, like actually putting this to use.
Exactly, yeah.
So this pseudo-number thing kind of messes with how well we can amplify these states.
Right.
So do we just hit a wall when we're trying to amplify certain SCSs?
Not really a wall, more like a few bumps in the road.
Okay.
You see these show up as like troughs on a fidelity graph.
Okay.
Think of it like this. You have a graph, and the higher up you go, the more accurate the amplification.
Got it.
So for SCSs, you see these dips in the line. Those are the troughs where the accuracy kind of takes a hit.
So we're talking about dips in accuracy.
Yeah.
But what's actually happening at the quantum level at these troughs? Like, why do they show up?
It all goes back to those unique properties that SCSs have.
Okay.
That whole pseudo-number thing really comes into play.
Right.
So depending on how the SCS starts out,
Okay.
how many components it's got, the phases involved, and which amplification method we're using, we're going to hit points where the accuracy drops.
So are some SCSs more prone to these dips than others?
Absolutely. Some combinations are just naturally more sensitive.
Okay.
It's this delicate balance between the SCS's initial state and how we're trying to amplify it.
This is all super interesting, but let's step back for a second.
Sure.
We've got these amplified quantum states, both HESs and SCSs.
Right.
But like, why does this even matter for someone who isn't a quantum physicist? What's the practical application here?
That's the million-dollar question. This leads us to a really important concept in quantum tech called quantum Fisher information.
Quantum Fisher information.
Yeah, it's a mouthful.
Okay. You're going to have to break that one down for me.
Basically, it's a way to measure how useful an amplified state would be for tasks like quantum phase estimation.
Okay, now you're just using big words.
It's all right.
Quantum phase estimation, what is that?
Imagine you're trying to measure a really, really tiny change in a wave's phase.
Okay.
Like if you had a perfectly still pond and you were trying to detect the tiniest ripple, quantum phase estimation is like having this incredibly precise instrument that can measure that ripple.
So we're talking about measuring things that are almost impossible to detect.
Exactly.
Okay, so why is this important?
Those tiny changes actually matter a lot in different quantum technologies.
Like what?
Well, think about super precise sensors that could pick up even the slightest variations in gravity.
Wow.
Or maybe predicting earthquakes by detecting changes in the Earth's magnetic field.
Okay, I see where you're going with this.
And of course, we can't forget about quantum computers.
Right.
They rely on these subtle changes too.
So quantum phase estimation is like the key to unlocking these technologies.
It's a big part of it, yeah.
So how do these amplified states help us out?
Well, think of amplifying a quantum state, like fine-tuning that super precise instrument we talked about.
Okay,
It makes it even better at detecting those tiny changes in the waves phase.
makes sense.
But here's where it gets interesting.
Oh, what's going on?
The paper found that for high-dimensional SCSs, the ones with tons of components,
Right.
quantum Fisher information doesn't behave as simply as it does for HESs.
So more curveballs from the SCSs?
Pretty much.
Does that mean there's no good way to amplify them for these applications?
Not necessarily, it just means we have to be more strategic.
Oh.
There's no single best way to amplify SCSs. It all depends on what we're trying to achieve with that specific SCS.
So it's all about finding the perfect match.
Yeah, you could say that.
The right amplification method for the right SCS, all depending on what you're trying to do.
That's a great way to put it.
So we've talked about amplifying HESs and all the things that make amplifying SCSs tricky.
Right.
But for our listeners who are maybe just starting to learn about quantum stuff,
Sure.
what's the big takeaway here? What does it all mean?
I think it really shows just how complex the quantum world is.
Okay.
Even when we're talking about something like amplifying a signal,
Yeah.
there's so much to think about.
Yeah.
So many little details that matter.
It's like we're still figuring out the rules of the game.
Exactly.
Yeah.
And that's part of what makes it so fascinating.
So as we get better at like fine-tuning these quantum instruments,
Yeah.
what are you most excited about? What's on the horizon?
Oh, man. There are so many possibilities.
Hit me with it.
Well, imagine being able to hear the faintest whispers of gravitational waves.
Yeah.
It would be like getting a glimpse of the universe right after the Big Bang.
That's incredible.
Or imagine sensors so precise They could pick up tiny changes in the Earth's magnetic field.
Okay.
Maybe we could even predict earthquakes before they happen.
Wow.
And we can't forget about quantum computers.
Right. How could those change?
If we can amplify the right quantum states,
Oh.
we could make them way more powerful.
Okay.
Imagine solving problems that seem impossible right now,
Yeah.
like developing new medicines or creating entirely new materials.
It's like we're on the edge of a whole new technological revolution.
I think we are.
And it's all thanks to these tiny quantum signals.
It all comes back to the quantum world.
Well, this has been amazing. We went from listening to quantum whispers to talking about changing the world.
It's been quite a journey.
Any final thoughts before we wrap things up?
Just that I think we're going to see even more surprises as we explore this quantum realm.
Yeah.
But those surprises will lead to new discoveries and incredible progress.
It's a journey worth taking.
Absolutely.
Well said. A huge thank you to our expert for explaining all of this to us.
It was my pleasure.
And to everyone listening, thanks for joining us on this deep dive into the quantum world. Until next time, keep exploring and stay curious. Okay, so like when you want to really get into something, really dive deep, That's what we're doing today, diving deep into the quantum world. Specifically, we're talking about making quantum states bigger.
Amplifying them.
Yeah, amplifying them. And why does size even matter when you're talking about something as small as a quantum state?
Well, think of it like this.
Okay.
Imagine you're trying to listen to a faraway radio station, and the signal is really faint. You want to amplify that signal so you can hear it better. Right?
Mm-hmm.
It's kind of the same idea with quantum states. A larger quantum state is more robust. It's less prone to being disturbed by all the noise in the quantum environment.
So turning up the volume so you can actually hear it over all the other noise.
Exactly.
So in a way, we're trying to make these quantum whispers shout.
You got it.
But I bet it's not as simple as just cranking up the volume knob on a radio.
No, you're right. It's a bit more delicate than that. Amplifying a quantum state without distorting it, that's a major challenge in quantum physics.
Oh.
And that's what makes this research paper we're diving into so fascinating.
Oh, yeah.
Yeah, it delves into different ways to amplify two very specific types of quantum states.
Yeah.
Hybrid entangled states.
Okay.
Or HESs for short, and superpositions of coherent states.
Got it.
Which we'll call SCSs.
Okay, HES and SCSs. So what in the quantum world is a hybrid entangled state? And more importantly, why should I care?
Well, imagine a light switch.
Okay.
It can be either on or off right, representing a discrete variable.
Right.
Now, picture a dimmer switch, which lets you choose a range of brightness levels that's a continuous variable.
Okay.
A hybrid entangled state is kind of like combining those two types of switches into a single quantum system.
Oh, wow. That's pretty cool. But how do you even begin to amplify something that seemingly exists in two states at once?
That's a great question, and this paper explores two main techniques for amplifying these HESs. The first one is called the photon addition then subtraction scheme,
Okay.
often shortened to the ARO scheme.
Kitschy. So what's the basic idea behind this photon addition then subtraction? It sounds like you're just putting something in and taking it right back out.
Yeah, it's a bit like subtly rearranging something to change its overall state without making it look any different.
Huh.
We carefully add a photon, a particle of light, to the HES,
Right.
and then very precisely remove one. This seemingly roundabout process actually bumps the state up to a higher energy level.
Uh-huh.
And the beauty of this method is that it yields very high fidelity, meaning the amplified state remains very true to the original.
Okay, so it's precise and reliable, but I'm guessing maybe not the most powerful method. What's the alternative for when you need a bigger oomph?
The alternative is what's called the successive photon addition scheme, or the O2 scheme for short. It's more of a brute force approach, where we essentially bombard the HES with energy to increase its amplitude. Think of it like pushing someone on a swing. Each push adds more energy, making them swing higher.
So more gain, but potentially at the cost of fidelity. It sounds like there's a trade-off between finesse and power.
You got it. There's a higher risk of distorting the original state with this method, but here's where things get really interesting.
Oh, yeah?
Yeah, the paper found that when applied to HES, both the precise R scheme and the brute force AA2 scheme behave remarkably similarly to how they would if you use them on simpler coherent states.
Now, why is that surprising? Didn't you say that HES are more complex than those simple coherent states?
Exactly. Because HESs have this intriguing blend of discrete and continuous variables, you'd expect them to react differently to amplification. But this research reveals an unexpected symmetry between these two seemingly very different types of quantum states.
So even though HESs seem more complex, they have this hidden simplicity when it comes to amplification. I'm starting to see why this paper caught your eye. Now, we've spent some time getting to know HESs, but what about those SCSs, the superpositions of coherent states? What makes them so special?
So superpositions of coherent states, SCSs, imagine a single quantum object,
Oh,
like a photon being in multiple places simultaneously.
okay.
It's already kind of mind-bending, right?
Yeah.
Now picture trying to make that blurry, multi-located object even bigger without ruining its delicate superposition.
Okay, I'm already feeling a little out of my depth, but I'm game if you are. What happens when you try to amplify something that's essentially in multiple places at once?
It gets wonderfully weird. Amplifying an SCS affects its presence, so to speak, in those multiple locations. Remember how we talked about fidelity, how closely the amplified state resembles the original?
Right.
Well, with SCSs, fidelity isn't straightforward. It's not uniform across the board. Some SCSs are much fussier than others when it comes to amplification.
Fussier. So some SCSs amplify more cleanly than others. What makes them so picky?
It's a combination of factors. One key factor the paper highlights is something called the qubit number.
Okay.
Think of it as an energy level label for different SCSs. A higher qubit number means the SCS has more energy to begin with.
Okay, so higher qubit number, higher energy. Got it. But how does that tie back into this whole fidelity issue during amplification?
Well, the research found that these fidelity dips, those moments, when the amplified state strays from the original, happen at different points depending on the qubit number. It's like each SCS has its own unique tolerance level for how much amplification it can handle before its fidelity is compromised.
So a high qubit number SCS might be fine with a lot of amplification, while a low qubit number SCS gets all distorted.
Precisely. And to make things even more interesting, the paper throws another variable into the mix. Dimensions, like as in parallel universes. Okay, now you've officially lost me. Not quite parallel universes in this context. But the concept of dimensions in quantum mechanics is definitely mind-bending. Essentially, higher dimensions mean there are more ways for these blurry, multi-located SCSs to potentially overlap and interfere with each other during amplification.
Okay, so we've got qubit numbers dictating tolerance and dimensions, adding another layer of complexity to how these SCSs interact during amplification. It sounds like trying to herd quantum cats. How do physicists even begin to control for all of this?
It is incredibly complex, and that's precisely what makes this research so groundbreaking. These physicists have managed to map out these intricate relationships between qubit number, dimension, and fidelity in a way that allows us to predict how different SCSs will behave during amplification. But here's a key takeaway they found. For SCSs with very large amplitudes, those that are already pretty loud to begin with, the differences between those two amplification methods we discussed, the R and the IR2, they actually start to fade away.
So at a certain point, those subtle differences between the precise photon addition and subtraction and the brute force approach don't really matter.
Exactly. It's like the sheer size of the SCS overwhelms those nuanced differences.
Yeah.
But now that we've explored how to make these quantum states bigger, let's shift gears and talk about how we actually measure their usefulness. After all, we want to know if these amplified states are actually good for something, right?
Absolutely. It's all well and good to make something bigger, but if it can't do anything useful, then what's the point? So how do we measure the oomph of an amplified quantum state?
That's where quantum Fisher information comes into play.
Okay.
It's a metric that quantifies how much information we can extract from a quantum state for specific tasks. Think of it as a measure of how much potential a state has for doing something practical.
Okay, so quantum Fisher information tells us if bigger actually means better in the quantum world.
You got it. In the case of this research, they were specifically looking at how useful these amplified states are for something called phase estimation.
Phase estimation, and there's a term I haven't heard before.
It's a fundamental concept in quantum mechanics, with applications in areas like quantum communication and sensing. Think of it as a way to precisely measure the difference between two quantum waves. It's like having a super accurate ruler for the quantum world.
Okay, so we're using quantum Fisher information, or quantum ruler, to see how good these amplified states are at this phase estimation thing. What did the researchers find? Is there a clear correlation, bigger state, more information?
That's the million-dollar question, and the answer, unfortunately, isn't as straightforward as we'd like. For HESs, those hybrid entangled states, it's pretty clear-cut. Higher quantum Fisher information generally translates to better amplification, but when we look at SCSs, particularly those in higher dimensions, the relationship gets messy.
Messy how? What's going on with SCSs that makes them such rule breakers? Messy how? What's going on with SCSs that makes them such rule breakers?
Well, it's like they just throw the rule book out the window.
Okay.
Remember how we talked about higher dimensions making things more complex for SCSs during amplification?
Right.
Well, it turns out those higher dimensions also mess up the neat relationship between size and usefulness that we see with HESs.
Okay, so it's not as simple as bigger state equals more information when it comes to SCSs in those higher dimensions. But quantum Fisher information is still giving us some clues, right? What's the takeaway for these rule-breaking SCSs?
Yeah, it's telling us that we can't just rely on these traditional metrics to predict how useful an amplified SCS will be. We need to dig deeper, consider those pesky Quetet numbers, dimensions, and how they all interplay. This paper has opened up a whole new avenue for understanding SCSs and their potential applications, especially when we move beyond simple phase estimation.
So it's like we've stumbled onto a whole new quantum playground, but the equipment comes with a manual that we're still trying to figure out. But that's half the fun of science, right? Discovering new puzzles to solve.
Absolutely. And this research has provided us with some really valuable tools for unraveling these quantum mysteries. It's reminding us that the quantum world is full of surprises, and sometimes the most intriguing discoveries come from those rule-breaking entities like SCSs.
Well, I always did have a soft spot for the rebels. So, as we wrap up our deep dive into the world of amplifying quantum states, what are some key takeaways you want our listeners to remember?
I think the biggest takeaway here is that it's all about finding the right tool for the job.
Okay.
Need to amplify a low-amplitude state with absolute precision. Photon addition, then subtraction. That OS scheme is your best bet.
Got it.
Looking for a bigger boost, and don't mind a little less fidelity. The brute force OSU scheme might be the way to go. But, and here's the kicker, those rules of thumb might not apply so neatly when we venture into the realm of SCSs, especially in those mind-bending higher dimensions.
Right. It's like SCSs are saying, we appreciate the toolkit, but we're going to need something a bit more quantum to handle our unique brand of weirdness.
Exactly. And that's what makes this research so exciting. It's pushing us to develop new tools and new ways of thinking to harness the full potential of these fascinating quantum systems.
So to sum it all up, amplifying quantum states is this balancing act, a delicate dance between gaining size and preserving fidelity with the rules of engagement shifting depending on the type of state that we're working with. But here's a final thought I'd like to leave you with. This paper focused on using quantum Fisher information to gauge the usefulness of these amplified states for phase estimation. But what about all the other potential applications out there? What if these amplified states, with all their quirks and complexities, hold the key to unlocking even more powerful quantum technologies that we haven't even dreamt of yet? Something to ponder as you navigate the ever-evolving quantum landscape. Until next time, keep exploring, keep asking questions, and most importantly, keep diving deep. Ever tried to make a faded old photo look, crisp and clear?
Yeah.
That's kind of what we're diving into today. Quantum amplification.
Okay.
The art of making quantum states bigger, but instead of Photoshop, we're talking photons. And trust me, quantum mechanics has way more rules than any photo editor.
It's true. You can't just hit enhance on these states.
Right.
What's fascinating is how tricky it is to amplify them without introducing errors, because of that inherent randomness in quantum systems.
Right. Okay. Our deep dive today takes us to Seoul National University, where researchers are figuring out how to amplify two very specific types of quantum states.
Okay.
Hybrid entangled states,
All right.
or HES for short, and superpositions of coherent states, which we'll call SCSs.
Got it. Imagine an HES, like a blurry photo where you can tell it's, say, a dog.
Okay.
That's the clear or discrete part of the state, but you can't make out the breed or size.
Right.
Those are the blurry continuous variables. Now, an SCS is more like stacking two perfectly clear photos on top of each other. It's like just slightly offset.
Okay.
Creating kind of an interference pattern.
Okay. I think I'm getting the picture.
Yeah.
Blurry dog versus slightly out of sync, double exposure.
Right.
But why would we even want to enlarge these quantum images in the first place?
That's the key question, right?
Yeah.
It's not about size for the sake of it. Amplifying these states could help unlock potential in fields like quantum computing, where, stronger signals mean more powerful calculations.
Right.
Or even lead to super precise measurements at, like, the tiniest scales.
So it's like boosting the signal so we can actually do something useful with it.
Exactly.
Okay. So this paper gets into two main amplification methods.
Yeah.
And they both involve manipulating photons, those tiny particles of light.
Right.
The first one, photon addition and then subtraction, sounds a bit like a contradiction.
It does, but think of it like fine-tuning a microscope. You add a bit of light to illuminate the sample, and then you might use a filter to subtract some, just to get the perfect contrast.
So it's all about getting the balance right.
Right.
What about the second method?
The second method, successive photon addition, is more straightforward.
Yeah.
Imagine shining a brighter light onto your blurry photo.
Okay.
But even here, we're talking about incredibly precise additions, not just blasting it with a floodlight.
Got it. But I'm guessing it's not as easy as it sounds. The paper mentioned these methods are probabilistic, not deterministic.
Right.
Does that mean they don't always work?
That's exactly what it means.
Okay.
And that's not a limitation of our technology. It's a fundamental principle of quantum mechanics.
Okay.
There's always an element of chance involved,
Wow.
even for the best quantum physicists out there.
It's like even with the best equipment, sometimes the quantum world just does its own thing.
Yeah, pretty much.
So how does this all work in practice with the HES, our blurry dog photo?
Here's where it gets interesting. Amplifying an HES is surprisingly similar to amplifying a regular clear photo, what we call a coherent state.
Okay.
It's like discovering that two seemingly different photo editing techniques actually rely on the same underlying principles.
Wait, so even though those states look totally different, the way we amplify them is basically the same?
In many ways, yes.
Mm-hmm.
For example, the researchers found that we can use the same calculations for fidelity. That's how close the amplified state is to the target.
Okay.
And gain, how much bigger we've managed to make it.
Right.
For both single images and these blurry, entangled ones.
That's pretty mind-blowing. And there's this Proposition 1 in the paper, which, to be honest, went a bit over my head, but it sounded like it reinforced this idea, something about applying filters.
Right. Proposition 1 is essentially saying that no matter what kind of filter or effect, we call them bosonic operators in the quantum world,
Right.
you apply to the HES, the result is the same as if you applied it to just one clear picture.
Wow.
This is a huge simplification because it means we can use a lot of the tools we already have for manipulating single quantum states to work with these more complex HES states.
So we can use the same tools for our blurry dog photos as we do for the single crisp images.
Exactly.
That simplifies things a lot. But if both methods work on HES, how do we know which one to use? It sounds like choosing between different lenses, each one has its own strengths.
That's a great analogy. It really depends on what you want to achieve. Let's break down each method a little further. So with the addition then subtraction method, you get higher fidelity,
Okay.
meaning your amplified state closely resembles the original, just like you'd want with a high-quality zoom on a photo, right?
Right.
It's the ideal approach when you're dealing with a very faint, low-amplitude state.
It's like giving that blurry dog photo a little boost in contrast without blowing out the details.
Right. Exactly. Now, on the other hand, the successive photon addition method, shining more light, gives you higher gain.
Okay.
That means you can make the amplitude significantly larger, although you might sacrifice some of that crisp fidelity.
So it's a trade-off. Fidelity for faint states, gain for when you need a bigger impact.
You've got it.
Oh.
And that's where a really cool concept comes in. Quantum Fisher information. Imagine trying to measure exactly how shifted those layered photos in the SCS are from each other.
Okay.
Quantum Fisher information tells us how effectively we can make those precise measurements using our amplified state.
It's like a measure of how much useful information survives the amplification process, even with those inevitable quantum quirks.
Precisely. And what the researchers found is, again, there's no one-size-fits-all answer. For low-amplitude HES, the addition then subtraction method works best for phase estimation. But for higher amplitudes, successive addition takes the lead.
Yeah.
And get this. At very high amplitude, the two methods become practically indistinguishable.
Quantum mechanics throws us a curveball again.
Yeah.
Okay, we've covered the blurry dog photos, the HES. But what happens when we want to enlarge those layered photo stacks, the SCSs? The paper makes it sound like things get even weirder there.
Weird is a good word for it. Amplifying SCSs is where this research really enters uncharted territory.
Okay.
Unlike with HES, we can't just apply the same formulas and expect predictable results.
Why is that? What makes SCSs so much trickier?
It comes down to the nature of the interference patterns created by those layered images.
Right.
Amplifying those patterns amplifies the complexity too.
Wow.
Even figuring out the fidelity and gain requires some serious mathematical acrobatics.
So instead of neat equations, we're stuck with, what, quantum guesswork?
Not quite.
Okay.
But the researchers did have to rely on complex numerical solutions, crunching numbers, to simulate how these SCSs behave when amplified. And surprise, surprise, they found some pretty unexpected results.
Like what? Do tell. I live for these quantum twists.
Well, remember how we talked about fidelity? How close the amplified state is to the ideal target.
Yeah, like how clear the enlarged photo is.
Right. Well, when they amplified SCSs using the addition then subtraction method, the fidelity graph showed a dip, a trough, as the amplitude increased.
Wait, a dip? You mean the fidelity actually got worse as they tried to make the state bigger? That seems counterintuitive.
It does, doesn't it?
Yeah.
It highlights a crucial difference between the quantum world and our everyday experience.
Okay.
Quantum states aren't just scaled-up versions of classical systems.
Yeah.
They play by their own bizarre rules.
Okay, so what's the explanation for this fidelity dip? Why would making the state bigger make it less accurate?
Think about it this way. At very low amplitudes, SCSs behave a lot like what we call number states.
Okay.
Imagine instead of seeing an entire image, you're just counting individual particles of light.
So it's like the difference between seeing a complete picture and just seeing the pixels that make it up.
Yeah. Exactly.
Uh-huh.
But as you increase the amplitude of an SCS, it transitions from that simple counting photons behavior to a more complex mixture of states.
Okay.
Right. And the amplification process ends up messing with that delicate balance, causing that dip in fidelity we see on the graph.
That's the gist of it. It's as if you're trying to enlarge a photo that's constantly flickering between different exposures.
Right.
The result isn't going to be pretty.
That makes sense.
Yeah.
And to make things even more interesting, I read that the successive photon addition method, the more direct amplification, actually creates even more pronounced troughs in the fidelity for certain types of SCSs.
You're right, it does.
Wow.
It goes to show that the relationship between the type of state you're amplifying, its initial properties, and the method you choose is far from straightforward.
Yeah.
There's a delicate dance between these factors that we're only beginning to understand.
So no easy answers then.
But if those fidelity troughs are throwing a wrench in our quantum plans, how do we even figure out the best way to amplify an SCS? Does our friend Quantum Fisher information come to the rescue here too? It's been a lifesaver so far.
Right.
But I'm sensing another "it depends" coming on.
Well, you're not wrong.
Okay.
Quantum Fisher information can be useful for SCSs.
Okay.
But it gets a little fuzzy,
Okay.
especially with higher dimensional states, those with lots of layers.
So our trusty compass is useless in this quantum jungle. What makes these higher dimensional states so finicky?
Remember how quantum Fisher information tells us how well an amplified state can be used for phase estimation?
Yeah.
Measuring those tiny shifts between our layered images?
Yeah, it's all about preserving that useful information.
Exactly.
Oh, wait.
The problem is with more layers, the quantum Fisher information starts to fluctuate wildly. It's like
Okay.
trying to read a compass in the middle of a magnetic storm. The needle jumps all over the place.
So it becomes less reliable as a guide for choosing the best amplification method for these complex states.
Unfortunately, yes.
Wow.
We're really entering the cutting edge of quantum manipulation here, and there are still many open questions.
It's like we're trying to write the instruction manual as we go along.
Pretty much.
So where does this leave us? If there's no magic formula, how do we navigate this quantum maze of amplification methods and unpredictable fidelity dips?
It all boils down to carefully considering the trade-offs for each situation.
Okay.
There's no one-size-fits-all answer in the quantum world.
So no amplify button for us, huh? It's more nuanced than that.
Much more. Let's recap what we've learned.
Okay.
Choosing the optimal amplification method hinges on a few key factors.
Okay.
First, what kind of quantum state are we dealing with? A blurry HES or a layered SCS?
It's like deciding whether to edit a slightly blurry photo or a complex image with multiple layers and effects.
Exactly.
Okay.
Then we need to consider the state's initial amplitude.
Right.
Are we starting with a faint whisper or a strong signal?
Faint signals might need a fidelity boost, while strong ones might prioritize gain.
Right.
Okay.
And finally, maybe most importantly, we have to ask ourselves what we want to do with the amplified state. Are we aiming for ultra-precise phase estimation for quantum sensors, or maybe high-fidelity states for complex quantum computations.
It's about choosing the right tool for the job.
Right.
Except in this case, the tools are quantum processes,
Mm.
and the job is manipulating the very fabric of reality.
And that's what makes this research so compelling. It underscores that even seemingly simple actions like making a quantum state bigger require careful thought and a deep understanding of the underlying physics.
Yeah.
We're not just scaling up classical systems, we're operating in a realm where amplification itself has profound implications.
This paper gave us a taste of just how complex amplification can be, and it raises some pretty mind-boggling questions about the future of quantum technologies.
Absolutely. If amplifying these relatively simple states is already this intricate, imagine the challenges and possibilities of manipulating even stranger, more exotic quantum states.
The states that could revolutionize computing, crack the code of quantum communication, or even reshape our understanding of the universe itself.
Exactly. And that, dear listener, is why we love taking these deep dives into the quantum world, uncovering its mysteries one amplification at a time.
Ever try to make a souffle rise higher by, like, just blasting the oven?
Yeah.
Total disaster, right?
Yeah, you'd end up with a very flat souffle.
Exactly. And it turns out quantum physics has a kind of similar problem. It's not always about bigger being better. Sometimes you need finesse.
Yeah.
So today we're going deep into the world of quantum amplification.
Okay.
We've got some seriously cool research someone sent us,
Right.
all about making quantum signals stronger, without,
Pumping up the volume too much?
well, yeah, without ruining their, their quantumness.
Right, right. Because quantum states, they're notoriously delicate.
Exactly.
Like trying to whisper a secret across a crowded room, you amplify it too much and the message gets all distorted.
Perfect analogy.
Yeah.
And that's exactly what these researchers are tackling, focusing on two, they're tricky types of quantum states. We've got hybrid entangled states,
Those are fun.
HES for short, and then
Yeah.
superpositions of coherent states.
Right.
Let's just call them SCS. It'll be easier.
Much easier.
So we've got HES and SCS.
And the fascinating thing is, they really behave quite differently when you try and amplify them. It's like they have almost distinct personalities.
You're giving attitude.
A little bit, a little bit.
Okay, so let's meet our quantum contestants here. First up, HES.
Okay.
How do we even picture this? So think of a light switch, right?
Okay. On or off?
On or off, very simple. Now entangle that with like a dimmer switch.
Well, yeah.
You've got that smooth range of brightness.
So you're intertwining something very black and white with something with a bit more nuance.
Exactly. Something
Right.
discrete with something continuous.
Yes, exactly. And the paper we're looking at, it gives this really neat image. Picture a single photon, right? So just this tiny little packet of light,
I'm picturing.
and it's linked to this whole wave of light. Like it's this weird quantum dance they're doing together.
My brain needs a dance partner just to picture that.
Right.
All right, so we've got this weird dance between a photon and a wave of light. That's HES.
Yeah.
But then we have SCS. Right. And it's like we're taking multiple waves of light, but then like messing with like their rhythm. Imagine shifting the peaks and troughs so they're overlapping in crazy ways.
It's like we're taking that single instrument, and now we're creating a whole symphony of light, right?
Oh.
Each wave is kind of playing a different note,
Mm.
and that results in this completely new sound, or in our case, a completely new quantum state.
I'm already hearing the cosmic orchestra tuning up.
Yeah.
So we've got these two strange states, HES and SCS.
Right.
How do the researchers even begin to amplify them? Where do they even start?
Well, they investigated two main techniques. Neither of them is perfect, which is where, it gets really interesting.
Okay.
The first one is very delicate, very, very precise. They add a photon, and then they take one away.
So they're being sneaky. They're like, oh, we're just going to borrow this energy for a second and give it right back.
Exactly. It's all about precision with this technique.
Okay.
The second method's a bit bolder.
Okay.
They just add two photons, one after the other.
Less subtle, more like a quantum power-up.
Exactly.
Just hit it with a blast of energy.
Yeah, exactly.
So which one wins? Is it the sneaking in or is it just blasting it with photons?
Well, that's what's really interesting because it depends on the state you're trying to amplify.
Okay, so are we going back to our...
Start with HES.
Okay, let's go back to HES. All right, so how does amplifying these hybrid entangled states actually work? Is it anything like, I don't know, trying to make a souffle rise with a hairdryer?
Well, that's it's not a bad analogy. What's really surprising here
Okay.
is that amplifying HES, it's actually remarkably similar to amplifying just a simple coherent state.
Really?
So just a single wave of light. Remember our symphony?
Yeah.
It's like we're just boosting the volume of one instrument instead of the whole orchestra.
So even though HES are way more complex than just a single wave of light,
Yeah.
they behave similarly when you try to like turn up the volume?
Yeah, exactly. And that actually simplifies things a lot, which is really cool.
Yep.
Because it means we can take what we already know about manipulating coherent states and apply that to these more complex hybrid states.
So we're saving ourselves some work here.
Exactly. A lot of time and effort in the quantum world.
Always a good thing.
Yes.
But even with that similarity, you mentioned neither amplification method is perfect.
Yeah, they both have their drawbacks.
So how do researchers even choose? Like if they've got HES, how do they know which way to go?
It's a real balancing act.
Okay.
They have to weigh two main factors, fidelity and gain.
Okay, so let's take those one at a time. What is fidelity in this?
Fidelity is basically, think of it like accuracy.
Okay.
How close is the amplified state to the exact state that we want?
Okay.
So the higher the fidelity, the more accurate the result.
So it's like if you had like a delicate artifact
Yeah.
and you're trying to make a copy,
Yeah.
you want it to be as close to that original as possible.
Exactly.
High fidelity copy.
Yes, precisely. And what they found is that the add then subtract method, remember that really careful one photon in, one photon out approach?
Yeah, that sneaky one.
Yes, exactly. That one tends to have higher fidelity, especially for states with smaller amplitudes.
Okay, so if you need that pinpoint accuracy,
That's the way to go.
go with the sneaky method.
Exactly.
But what about gain?
Yeah.
What does that even mean in this context?
Gain, think of that as strength.
Okay.
So how much did we actually amplify the signal? You know, how loud did we make it?
Okay.
And for gain, the double photon method actually does better.
Really?
It might not be as precise,
Okay.
but it packs more of a punch, especially as those amplitudes get larger and larger.
So it's a trade-off. Precision versus power.
Yeah.
So how do you know which one to, like, how do researchers even choose?
Well, they use this thing called quantum Fisher information.
Okay.
And think of this as kind of like a measure of how much useful information the amplified state actually carries, especially for doing something like, can we figure out the angle of a quantum state, you know, its phase?
Okay, so it's a measure of, like, how much this amplified state can actually tell us.
Exactly. How much potential it has to unlock further quantum secrets.
I like it.
And when they look at this quantum Fisher information,
Okay.
they actually found some very clear results. So for smaller amplitudes, where that precision is really key, the add and subtract method, it still reigns supreme.
Okay.
But as you start cranking up the amplitude,
Yeah.
that double photon method, even though it's a little messier, it actually becomes more and more useful.
Really?
And at very, very high amplitudes, they're almost neck and neck.
So there's like a tipping point where it's just like, all right, blast it. We're going for power here.
Exactly. Exactly.
That's fascinating.
It is really interesting to see how those two methods play out.
Okay, so that was HES, but we also have SCS.
Right.
And you mentioned earlier that amplifying those is a whole other like ball game. What makes them so different?
So amplifying SCS, it's a little bit like trying to predict the weather. It really depends heavily on the specific type of SCS that you're dealing with.
Oh, okay.
So unlike HES,
Yeah.
where the fidelity really depended mainly on the amplitude,
Okay.
SCS fidelity, it also depends on something called the qubit number.
The what number?
The qubit number.
Okay. You're losing me a little bit.
Yeah.
What is a qubit number?
So think of the qubit number as kind of like a quantum fingerprint
Okay.
that's unique to each type of SCS.
Oh, okay.
So it's like this extra layer of complexity
Okay.
because it influences how that state is going to react when you try to amplify it.
So it's not like a one-size-fits-all approach with SCS. We have to like know a little bit more about it before we start.
Exactly. Exactly. You have to consider its unique fingerprint.
Okay. So what does that actually mean for like fidelity? You said it gets really wild.
Yeah.
How so?
So as you increase the amplitude, the fidelity of the amplified state, it doesn't just go up smoothly. You start seeing these weird dips in fidelity as the amplitude increases.
Wait, so increasing the amplitude can actually backfire
It can. It can.
and make it less accurate?
Yes.
But that doesn't make sense. Why would that happen?
That's the million-dollar question, right?
Yeah.
And it really highlights just how sensitive these SCS states are to being manipulated
Okay.
compared to the HES.
So they're just very finicky.
Very, very finicky.
Okay.
And it's not just fidelity either. Gain also shows some really unexpected behavior with certain types of SCS.
So it's a mess.
It's complex, but it's a puzzle that researchers are really trying to piece together.
So with HES, we've got a good understanding of how these two methods work, but with SCS, it's like, who knows?
It's a bit more of a free-for-all.
Yeah, it depends on their personality.
It really does, yeah. Each SCS state is its own beast.
So that's how we amplify them. But what does that mean for actually using these states?
That's a great question.
Like, how do researchers make sense of all of this?
Yeah, and that's what we're going to dive into in part 3.
Okay.
The good news is,
Okay.
even with all this complexity, there's some really clear takeaways. And even more exciting, there's some amazing potential applications for these amplified states.
Okay, well, let's get to it then. So we've been deep into this quantum world.
Yeah.
Hybrid entangled states, superpositions of coherent states.
Right.
I gotta say, my brain is kind of like still buzzing from all the like twists and turns.
It's a wild ride for sure.
Yeah.
We've got these two like completely different quantum states and how they react to amplification. HES, surprisingly predictable.
Okay.
But those SCS, man, they keep us on our toes.
Yeah, they're trouble. It's like HES, they're the well-behaved students in quantum class, and SCS, they're the rebels, always like pushing the boundaries.
That's a great way to put it. But
yeah.
Before we get too lost in all the theoretical stuff,
Okay.
let's bring it back down to earth for a sec.
Okay.
Why should we even care about amplifying these like bizarre quantum states?
Yeah, that's a fair question. We've been in the weeds here talking about photons and phases, fidelity.
Right, right.
But like, how does any of this impact us in like real life?
So this research, it's not just about like messing with tiny particles of light. It's really about this whole new world of technology and what's possible.
Like
imagine a world with ultra precise medical imaging. So we could detect diseases like way, way earlier.
Okay.
Using quantum sensors that are like exponentially more sensitive than anything we have today.
Catching diseases earlier, developing better treatments. I mean, that's
exactly
life-changing stuff.
That's just the start, right?
Okay.
Think about unbreakable quantum communication where information is like completely secure. No eavesdropping, even in theory.
Okay, no more like hackers stealing our data.
Exactly.
That's pretty huge.
Or picture this, right?
Okay.
Materials with unheard of properties, like superconductors that work at room temperature.
Wait, hold on. Room temperature superconductors? That would change like everything.
Revolutionize electronics, how we produce energy, everything.
Okay, so now you're talking like seriously futuristic stuff. But let's be real. What are the hurdles here? How do we actually get there from, these tiny experiments?
So scaling up, that's a big one, right?
Okay.
We've been talking about these relatively small systems.
Right.
To make these technologies practical, we need to figure out how to amplify and control these states in like much bigger, more complex environments.
So we figured out how to like bake a cupcake.
Yeah.
But now we need to make a 5-tier wedding cake with the same like level of precision.
Exactly. Exactly. And those quantum systems, just like your cake, they're incredibly delicate. There's another big challenge.
Okay.
Decoherence.
Okay, decoherence. Remind me what that was again.
So remember how sensitive these quantum states are? Any little interaction with like their surroundings, it can mess them up.
Okay.
They lose their special properties.
So it's like trying to build a sandcastle on a windy beach. One gust of wind.
Yeah, exactly.
You're done.
It all falls apart.
Okay.
So researchers are working really hard to figure out how to shield these amplified states from all that noise, create these really isolated environments where those quantum behaviors can actually like survive.
So we're still in the early stages, but it sounds like there's like a ton of potential here. So like for our listeners who are like trying to keep up with all this, what's the like most important thing to remember?
Remember this research. It's not just about like equations and abstract ideas.
Okay.
It's about pushing the boundaries of what's possible and using that like weirdness of the quantum world to actually solve real problems.
Making the impossible and making it doable.
Exactly.
That's what makes it so cool.
It's incredibly exciting, right? The future's wide open. Who knows what other bizarre quantum states are out there just waiting to be discovered?
It's like we've opened the door, just a crack.
Yeah.
And we've seen like a little bit of the light.
Exactly. Who knows what we'll find?
It's going to be a wild ride. Well, thanks for joining us for this deep dive.
My pleasure.
into the world of quantum amplification. And until next time, keep those minds curious.